Our next lesson is about properties of parallelograms. So again, we're using the tools we have developed about proving triangles to be congruent to now prove some properties about parallelograms. In this lesson, we'll hit one CCRSM standard, but there's a lot here. We will prove theorems about parallelograms, and the theorems include opposite sides are congruent, opposite angles are congruent, the diagonals of a parallelogram bisect each other, and rectangles are parallelograms with congruent diagonals. Now, this word include does mean that there's more about parallelograms you have to prove, but for this video, I'm going to stick to these four. Let's get started. As always, you should have your student materials in front of you. We will start this lesson by talking about example 1, which will cover the first 2 bullet points in our standard. Example 1 says, if a quadrilateral is a parallelogram, then its opposite sides and angles are equal in measure. This is exactly what was mentioned in the first 2 bullet points of our standard. Now, this is a conditional statement with an if and a then, and this part is what gives you the given. So we're given a quadrilateral. And to make this easier for us, I'm going to name the quadrilateral A, B, C, D. So I'm given parallelogram ABCD, which means I can use any property of parallelograms, and right now the only thing I can really use is the fact that the opposite sides are parallel, because that's how a parallelogram is defined. The other part, the then part, is where you get your prove statement. I will start with the given. The next step is to use the given. So use something from the given to tell me something about sides and angles. And I'm next going to mention the opposite sides are parallel, because that's how we define a parallelogram, and that must be useful somehow in this proof. So I will say that segment AB must be parallel to segment DC, and segment AD must be parallel to segment BC, because it's a parallelogram. And I will draw on the diagram. Okay, so I'll go one step further with this and tell me what do parallel lines tell me about sides and angles. And hopefully by now you're noticing that whenever we have parallel lines, we begin to look for alternate interior angles. Now, first looking at AB and DC, and looking at DB as a transversal, then I have these angles right here, angle ABD, 3 letters, the middle letters of the vertex, and angle CDB are congruent because they're alternate interior angles. Also, if we look at AD as being parallel lines, and again DB as the transversal, we also have ADB being congruent to CBD for the exact same reason. They're alternate interior angles. That's everything I can get from the given, from parallelogram ABCD and the auxiliary line. Now I would like to just, scroll up and write some more things at the bottom, but I can't because of the program I'm using. So I'm gonna have to erase the top part of this proof. Hopefully it's written in your notes. If not, then pause the video and jot these down. But I'm gonna have to erase this so I have more space to write. And now I look at the diagram and say, what is in the diagram that I can use? And I'm assuming that by now most of you are really good at noticing the reflexive property. That DB is in both triangles and it's congruent to itself. So the measure of DB is equal to the measure of DB by the reflexive property. Now, hopefully you notice we have angle, side, angle, and angle, side, angle. And so these triangles are congruent by angle, side, angle. A corresponds with C B corresponds with D, and D corresponds with B. All right, now that I have congruent triangles, all the corresponding sides and all the corresponding angles are congruent, and that's what really gets us to our proof statement. I can next say that AB is equal to DC because they're corresponding sides. I can say that AD is equal to BC because they're corresponding sides. I can say the measure of angle A is equal to the measure of angle C. And this one's a little more of a stretch because of notation. So angle B is this whole angle, and angle D is this whole angle. And I hope it's not too big of a jump to say, well, you know, the parts are congruent to the other parts, and so angle B must be congruent to angle D. I hope that's okay to make that jump, even though it could take me more steps to be more precise with that. I'm just going to finish it off with saying measure of angle B is equal to the measure of angle D because corresponding sides and angles in congruent triangles will also be congruent. Okay, that is the whole proof, proving that the opposite sides are equal in measure for a parallelogram and the opposite angles are equal in measure in a parallelogram. The next proof we'll do is example 2, which hits the next bullet point in our standard. Again, if a quadrilateral is a parallelogram, then the diagonals bisect each other. Again, the if part gives us the given, and I will name this just for convenience. So I'm given parallelogram ABCD. The then part gives me the proof statement. The diagonals will bisect each other. Now, to know what that means, I'm going to draw in the diagonals AC and BD, and if the diagonals bisect each other, then they cut each other in half. That means that AE must be equal to EC, and DE is equal to EB. That's what it means for the diagonals to bisect each other, is they cut each other in half. The way we start this is like we start most proofs, and we start with the given. I will next use some parallel lines. I will say that AD is parallel to BC, and I will draw on the diagram. Okay, and we could also say that AB is parallel to DC, but actually that won't be useful for me in the proof. I'm now going to use the thing we proved in example 1 and say that the opposite sides must be congruent because it's a parallelogram. And I can use that because I've just proved it to be true for all parallelograms. Again, I'll draw on the diagram. I will next use some properties of parallel lines. If I think about AD being parallel to BC, and I think about AC being a transversal, then I have some alternate interior angles. This angle, angle DAC, is an alternate interior angle with angle BCA. So they must be equal in measure because the lines are parallel. And if we now think about segment BD being a transversal, then I also have angle ADE being congruent to angle CBE because they're also alternate interior angles. At this point, we have enough to prove the triangles are congruent by angle, side, angle, angle, side, angle. But I'm out of space, and so you should leave this on your page. I would like to scroll up, but I can't. I'm going to erase this to have more space to write, but just write the things I write next below what's already written here. All right, next I'll say the triangles are congruent by angle, side, angle. A corresponds with C, D corresponds with B, and E corresponds with itself. And now that the triangles are congruent, all the corresponding sides and angles are congruent. Specifically, AE and EC are corresponding sides, and DE and EB are corresponding sides. And that's it. We've proved that the diagonals bisect each other because we've proved that AE and EC are equal and DE and EB are equal. The next proof we'll do together is example 3. We are given that if the parallelogram is a rectangle, then the diagonals are equal in length. So again, the if part gives us the given, and I will name this rectangle A, B, C, D, just for ease. And one more thing to point out is because a rectangle is a parallelogram, I still can use all the properties of parallelograms that I've proved in the last 2 examples. Now, the then part gives me the prove statement that diagonals are equal in length. Now I'm going to draw in the diagonals so I can talk about them. Now we start this proof, as we do every proof, with the given. Now before I get too much further in this proof, I want to point out that I'll be using triangle ADC, this triangle, and triangle BCD as the 2 triangles that I'll prove congruent, because they have diagonals as one of the sides, and I can prove that these 2 triangles are congruent, and that's kind of where I'm going in my proof, just to give you a heads up. Now, one property of rectangles, at least the definition of rectangles, that I've not shared yet in class, is that it's a quadrilateral, meaning 4 sides, with 4 right angles. That's the definition of a rectangle. So I will use that definition to say that ADC, this angle, which I'll draw up here, is congruent to BCD, this angle right here, which is right here, because they're both right angles. Next, I will use a property of parallelograms and say that segment AD must be congruent to segment BC because they are opposite sides in a parallelogram. And I will draw on the diagram. Now finally, this does not look like the way we usually see it, but DC is in both triangles, right? That's the same segment in both triangles, and so by the reflexive property, DC is congruent to DC. Again, we were looking at this triangle and this triangle, and hopefully you see we have side, angle, side, side, angle, side. So these triangles are congruent by side, angle, side. A corresponds with B, D corresponds with C, and C corresponds with D. And now that I have congruent triangles, all the corresponding sides and angles are congruent. Specifically, AC is equal to BD. I'm out of room, but corresponding sides of congruent triangles. And that's the proof to prove that the diagonals are equal in length in a rectangle. So this video was about properties of parallelograms. We proved these 4 properties. Thank you for watching.